Good morning, students. In the last class, we have discussed about the DC characteristics of Opamp. Coming to the DC characteristics of Opamp, we have studied about input offset voltage, input offset current, input bias current, and input resistance, output resistance, and total output offset voltage. So we have observed the input offset voltage, output offset voltage, input offset current, input bias current, input resistance, output resistance, and total output offset voltage. So coming to this, in the last classes we have discussed about how to measure the CMRR, how to measure the input offset voltage, how to measure the power supply rejection ratio, and also how to measure the input resistance. Now in this class we are going to observe how to measure the output resistance. So for measuring the output resistance, here we are going to consider this circuit. So here you can see the circuit. This is the circuit we are going to consider, and in this circuit you can see this is nothing but the equivalent circuit for an operational amplifier, in which we are going to consider VA as input voltage and RI as input resistance, and AOL into VI as the gain of the operational amplifier. So AOL is the open loop voltage gain, nothing but, into VI is the input voltage what we are going to apply here, and R0 is the resistance. So for this circuit, we are going to connect a resistor RL. So through a switch, if RL is connected, then if RL is connected, what will be the current? What will be the value of output resistance? And if RL is removed, what will be the value of output resistance? We are going to see. So first, output resistance is measured between the output terminal and the ground. So where this output resistance is measured, that is measured between output resistance, output terminal. That is, this is the output terminal. From this to the ground, we are going to measure the output resistance. So when the switch is connected, what happens? When the switch is open, the resistance is infinite. So when switch is open, we can say that this is open circuit. It acts as a output acts as a open circuit. That means open circuit resistance is infinite. So from that we can say that the open loop voltage gain is equal to output voltage divided by input voltage. So AOL is equal to V naught by VI. So this is how when switch is open we are going to get this equation. So when switch is closed, then this RL, this resistance RL is connected to the operational amplifier. When switch is closed, this resistance RL is connected to the operational amplifier, and then when this resistance connected to the operational amplifier, then operational amplifier, then this resistance will be in parallel with R0. So for that reason, we are going to use the voltage division rule, and we are going to write this equation for V0 as V0 is equal to AOL into VI. We know that this equation AOL into VI, this is the source which is going to act here. Source into opposite resistance, that is RL divided by the total resistance in this path, R0 plus RL. So AOL into VI into RL divided by R0 plus RL. So the gain will be now, so the gain by connecting this load resistance, the gain will change. So for that reason, we are going to consider the gain as AOL dash. We are going to consider the gain as AOL dash, and the new gain AOL dash, which is equal to, so we are bringing this VI, this input voltage VI to left hand side, and then it becomes V naught by VI. This is nothing but the new gain, that is AOL dash. So we are going to consider now AOL dash. So AOL dash is equal to, so what will be having here, AOL into RL, AOL into RL divided by R0 plus RL. So we have bring this VI to left hand side, so which becomes V0 by VI. So we are going to write that as AOL dash. We are going to write that equation as AOL dash. So this becomes AOL is equal to, AOL dash is equal to, finally we are going to obtain by solving the equation. So we are going to obtain AOL dash is equal to AOL into RL divided by R0 plus RL. So by solving this equation, we are going to get the value of R0. So R naught is equal to R naught is equal to, then we are going to get R naught is equal to AOL by AOL dash minus 1 divided into RL. So this is the equation we are going to get by solving this. So finally, in this way, if we know the value of AOL and AOL dash and RL value, then we can measure the value of output resistance. So how to find this AOL and AOL dash? So by opening the switch and measuring the already we know that VI, and we are going to calculate and we are going to measure the V naught. So from that equation, from this equation, we can obtain AOL. So here you can see this. For measuring AOL, we are opening the switch, yes, and then we are going to measure the output voltage with the help of multimeter, and whatever we are applying the input voltage is nothing but we know that the magnitude of the input voltage, and then by measuring those two we can find the value of AOL, and then by connecting this RL, and that means we are going to close the switch S, and then we are going to calculate the V naught. Then AOL dash can be calculated. So how we are going to calculate the AOL dash? We know the AOL already, we have calculated the AOL into RL divided by R naught plus RL. So for finding this R naught, we know the AOL, and we are going to find the AOL dash by connecting this switch. So by connecting that switch, we are going to find the AOL dash value also. How we are going to obtain the AOL dash? So how we are going to connect the AOL dash? Then this AOL dash can be obtained by connecting this switch S. So when this RL is connected, we can calculate the AOL dash. We can calculate the V naught. That means we can measure the output voltage V naught, and we know already we know the value of Vi. So we will obtain the AOL dash. For by obtaining the AOL and AOL dash, we can obtain the value of R naught. So in this way, we are going to measure the value of output resistance R naught. So this is the circuit we are going to consider for measuring the output resistance, and this is how we are going to measure the output resistance by connecting a RL resistor. So for an operational amplifier, practically we are going to find the output resistance by using this method. Next, measurement of total output offset voltage. So next concept is total output offset voltage. So we now only we are going to use this total output offset voltage. Before we have not discussed about this total output offset voltage. So what is this total output offset voltage? We are going to see now. So what is this total output offset voltage? Output offset voltage. So already we have studied about input bias current, input offset current, and uh, input offset current, and as well as input bias current, input offset current, as well as input offset voltage. So this total output offset voltage is due to input offset voltage as well as due to input offset current. So this is due to input offset voltage as well as due to input offset current. And the output offset voltage is due to bias current. So first we are going to see the output offset voltage due to input offset voltage. So output offset voltage is due to input offset voltage. Here in the we are going to consider this circuit, and here you can see the operational amplifier in which it is having two terminals, inverting terminal, non-inverting terminal plus VCC minus VE, and this is output terminal. These two are the input terminals. So inverting terminal is given to a given output for inverting terminal. We are applying a feedback through a feedback resistor RF, and as well as through R1 we are going to make it ground, and this node we are going to consider as V2. And for non-inverting terminal, we are going to take a RM resistor. That is, this RM resistor is nothing but a compensating resistor. So this RM resistor is nothing but RM value is nothing but the parallel combination of these two resistors, R1 and RF. So RM value can be considered as the parallel combination of these two values, R1 and RF. So that is nothing but RM is equal to R1 into RF divided by R1 plus RF. So by considering this resistor, and we are going to connect this resistance at the non-inverting terminal, and this node we are going to consider as V1. First we are going to measure the output offset voltage due to input offset voltage. Output offset voltage is due to input offset voltage, and we have studied here that output offset voltage is due to two parameters, that is input offset voltage and input offset current. So first we are going to measure the output offset voltage due to input offset voltage. So output offset voltage is due to input offset voltage can be represented with V double naught, and this is input offset voltage that can be obtained by VIO into 1 plus RF by R1. VIO into 1 plus RF by R1, then where VIO is input offset voltage into 1 plus RF by R1. RF by R1 is nothing but feedback resistance divided by the resistance R1, which is connected to the inverting terminal, So this we keep it aside, and this we are going to consider as one of the equation. And next, we are going to see output offset voltage is due to input offset current. So output offset voltage is due to input offset current or input bias current we can consider. So input offset current, here we are having two input terminals, that is IB1 as well as IB2. So first we are going to consider IB1 as well as IB2. So when we are going to consider IB1, now we can say that VIO2 due to input offset voltage, sorry, the output offset voltage due to the current which will be given by VOIB. VOIB, we are going to consider that as VOIB, which is equal to RF into IB1 minus IB2. This is nothing but input bias current. You know that bias current is nothing but IB1 minus IB2. Then we are going to consider IB1 minus IB2 as IIO, input offset current, which is nothing but input offset current. V not IB is equal to RF into input offset current. By obtaining that, the total output offset voltage, which is going to depend upon input offset voltage as well as input offset current. So total output offset voltage we are going to determine, we are going to write that total output offset voltage as VOOT, which is equal to input offset current into, sorry, input offset voltage into 1 plus RF by R1 and plus RF into II naught. So here you can see this equation is due to input offset voltage. That means output offset voltage due to input offset voltage plus output offset voltage due to input bias current or input offset current. So the total output offset voltage is given by the combination of these two offset voltages, output offset voltage due to input offset voltage as well as output offset voltage due to input offset current. So two offset voltages are of different polarities. If two, so we have found this two offset voltages. So if those two are having different polarities, then the total output offset voltage for an operational amplifier will be very small. That means here we can see that VIO is already, we have discussed that VIO is in the order of millivolts, and whereas input offset current is in the order of nanoamperes, very small values. These two are very small values. Finally, the output offset voltage will be, total output offset voltage will be also a very small value. So with this we are going to measure the total output offset voltage. So we can measure the total output offset voltage. How we are going to measure means, first we are going to measure the input offset voltage. How to measure the input offset voltage we have seen in the last classes. So first we are going to measure the input offset voltage. If we know the value of RF and R1, and if we measure the value of input offset current, then we can measure the value of total output offset voltage, which is going to depend upon input offset voltage value, input offset current value, whereas feedback resistance and as well as resistance R1. So this is how we are going to measure the total output offset voltage for an operational amplifier. And next, measurement of slew rate. So this slew rate. So slew rate is nothing but the maximum rate of change of output voltage. So slew rate is nothing but the maximum rate of change of output voltage. So which is given by S is equal to change in output voltage divided by change with respect to the time. Change in output voltage with respect to the time. So for that, we are going to consider the operational amplifier, this circuit for an operational amplifier. In this, we are going to we are going to make the inverting terminal which is shorted to the output terminal. That is nothing but output is directly connected to the inverting terminal for an operational amplifier. And for the non-inverting terminal, we are going to apply a square wave. So then this is going to act as, here you can consider this is going to act as a voltage follower or unity gain circuit, unity gain amplifier. So which is going to provide output gain. So that is unity gain means that is output is equal to input. So which is going to provide, which is going to act as a buffer, nothing but it, whatever the input signal we have given will be obtained at the output without any changes. So there will be a small change in the output voltage as we are applying here the square wave. So see here, you can see here, this is a square wave we have applied for a non-inverting terminal. Then we are going to obtain a waveform which is having a slight deviation in the square wave. So this deviation you can observe from this graph. You can see here there will be a change in output voltage. So here this change in output voltage we are going to consider as delta V naught, and change in time period, here you can see there will be a slope. So here actually we are going to apply a square wave, but here that square wave is going to change like a ramp signal. You can see here this is going linearly, this is going to increase, not at a time instant it is not going to change its state. So this deviation is going to be considered as delta t, that is change in the time period. So by measuring the value of this v naught, and also by measuring the value of this delta t, so we can find the value of slew rate. So for the slew rate, so slew rate is given by change in output voltage divided by change in time period. By applying a square wave, so how we are going to calculate here? So by applying a square wave, we are going to calculate the slew rate. So slew rate, applying a square wave to a non-inverting terminal, then by increasing the frequency. So how we are going to calculate? So we are going to slightly increase the frequency of the input signal, input square wave what we have given. So when we are giving the input square wave, input when we are applying this input square wave, and then we are going to increase the frequency of the input signal slightly, we are going to increase slowly. So when we are going to increase the frequency, there will be we are going to observe the output signal in the CRO. So then we can find at low frequencies it may there may be no deviation. So when we are going to change at a particular frequencies, we can find the change that is nothing but as a slope. This type of slope you can observe here. So this type of slope, when we are going to observe this type of slope, then we are going to calculate that slope time period as well as the output voltage from peak to peak voltage we are going to consider. So we are going to measure in the CRO, and then we are going, if we observe these two values, if you know these two values, then we can calculate the slew rate for a particular operational amplifier. For any operational amplifier, you are going to consider this circuit, and we are going to measure the slew rate for an operational amplifier. So that is, this is how we are going to measure the slew rate for an operational amplifier. And next so by obtaining the change in the output voltage and the time period of the signal, then we are going to calculate the slew rate for an operational amplifier. So next concept is, with this concept we have completed the measurement of DC characteristics of Opamp. So the slew rate comes under AC characteristics, leave the slew rate, and rest of those comes under DC characteristics. Those are nothing but input bias current, input offset current, input offset voltage, power supply rejection ratio, and CMRR, common mode rejection ratio, and then output resistance, how to calculate how to measure the output resistance, and how to measure the input resistance also we have seen, and also how to measure the slew rate we have observed this. So by this how what are the different DC characteristics we have known, and also what are the how to measure those different characteristics, DC characteristics for an operational amplifier, we have observed that. So if you want to measure this becomes we can do this as an experiment in the Lica linear IC applications lab also. So next AC characteristics. Next, coming to the AC characteristics for an operational amplifier. So in this AC characteristics for an operational amplifier, So we are going to consider the frequency response of operational amplifier. So AC characteristics means, so we are going to apply an AC signal for an operational amplifier and see how this operational amplifier is going to perform for the AC signal what we have given. So ideally, for an operational amplifier, ideally, if we consider the op-amp as the ideal one, then it must operate similarly. It must operate similarly at zero frequencies, from nothing but from zero frequency to infinite frequency. It must operate in the same manner. There must be no change in the operation of the operational amplifier. That means there must be no change in the performance of the operational amplifier if the frequency of the signal has been changed. That means if we change ante manamu nothing but if you change the value of the frequency from 0 hertz to maximum frequency, let us say that is 100 megahertz or 1000 megahertz or 1 gigahertz, around that. So if you change the frequency from 0 to some 10 megahertz also, the op-amp must produce the same output voltage for 0 hertz frequency as well as for 10 megahertz frequency. So this is the ideal characteristics of op-amp. But practically, it may not be possible. It may not possible practically because there will be several factors affecting the operation of several factors affecting the performance of operational amplifier, practical operational amplifier. That is. Mainly nothing but the resistance factors, the capacitance factor is the main factor. So here, why this capacitance is going to exist, as already we have studied in the first chapter itself, operational amplifier. In that operational amplifier, we have observed the four stages. That is, the first two stages consists of differential amplifier. So we are going to couple the first two stages directly. So we are not going to use any capacitor in between them. But how this capacitor is going to exist means, in the fabrication process itself, the capacitance is nothing but two conducting materials separated by an insulating material. Whenever the two conducting materials separated by an insulating material is there, then there exists a capacitance. So because of this, when four stages, we have studied about the four stages in an operational amplifier. That is the first stage, second stage, and third one is level shifter stage, and fourth one is push pull amplifier stage. These four stages are coupled together. So there will be three connections. From first stage to second stage, one connection will be there, and from second to third, another connection will be there, and third to fourth, there will be another connection. That means three stages are coupled together. So at this coupling, there may be a capacitance effect. There may be a capacitance effect when these three stages are coupled together. So this capacitance is going to affect the frequency response of operational amplifier. That means this capacitance is uh, going to affect the performance of that is AC characteristics, AC performance of operational amplifier. Due to this capacitance effect, we are having three corner frequencies for this operational amplifier. Why three corner frequencies? Because there is three stages, three coupling stages. So what we have studied now. So between first stage and second stage, second to third, and third to fourth. So because of this, there will be three corner frequencies for a operational amplifier. So first we are going to consider a single corner frequency. First we are going to consider single corner frequency for an operational amplifier, and we are going to observe the how this gain is going to be affected for an operational amplifier, and this how this gain is going to depend upon the frequency of the operational amplifier. So we are going to see now. So hence we know that the output voltage. So by for this AC characteristics, we are going to consider the equivalent circuit for an operational amplifier. So this is the equivalent circuit for an operational amplifier. So in this we are having V1 and V2 are the input terminals. VD is nothing but the differential voltage, and RI is the input resistance, and equivalent VD is the source, and R naught is the output resistance. And here we are going to consider a single capacitor, and we are going to find the effect of this capacitance on the performance of operational amplifier. So for this circuit, we are going to write the equation. We are going to consider V naught here. So V naught is equal to OL into VD. This is the factor. So this factor we are going to write here, AOL into VD divided by J 2 pi FC into R naught plus 1. So for obtaining that, so how we are going to obtain this equation means, how we are going to obtain this equation by considering the capacitance. So for this capacitance, we are going to see the, if you have any doubt, you can observe here this capacitance effect. So you can observe here. So here we can observe this is the circuit we are going to consider, and in this circuit we are going to see here V naught is equal to, so output voltage V naught is equal to minus JXC. That is nothing but here we are going to consider XC as the reactance of the capacitor. So minus JXC AOL into VD, AOL into VD, this is the voltage source, into opposite reactance, that is minus JXC, divided by the total resistance in the total reactance or resistance in this path R naught minus JXC. So with this equation we are going to write V naught. So then by writing this equation, we know that the reactance of the capacitor XC is given by 1 by 2 pi FC, and minus J can be written as 1 by J. So we are going to write this equation as, so in the place of XC we are going to write 1 by 2 pi fc, nothing but in the place of minus j we are going to write j. So v naught is equal to 1 by j 2 pi fc into AOL into VD divided by R naught plus 1 by j 2 pi fc. So by solving that equation, so you are going to get v naught is equal to AOL into VD divided by, so yeah, v naught is equal to AOL into VD divided by j 2 pi fc into R naught. So then from that we can write A is equal to, the gain A is equal to output by input, that is V naught by VD, which is equal to AOL divided by J2 pi FC into R naught. This is how we are going to obtain the value of AOL. So the value of AOL. Hence, hence we can, hence the gain will be given by A is equal to V naught by VD, which is equal to AOL by 1 by J2 pi FC into R naught. Hence F1 is equal to 1 by 2 pi FC into R naught. So here we are going to consider F1 as the corner frequency due to this capacitance effect, and this is the corner frequency we are going to obtain. And for this F1, so this F1 is going to depend upon 1 by 2 pi FC into R naught. So this F1, the frequency F1 is going to depend upon 1 by 2 pi FC into R naught. So, so we are going to replace this J 2 pi FC into R naught. So 2 pi FC into R naught with F1. So then this A will become AOL divided by 1 by J into F by F1. So if we consider the magnitude of the gain, then it will be AOL divided by root of 1 plus F by F1 whole square, 1 plus F by F1 whole square. So this is the corner frequency F1. So up to here you can see this is the frequency response with by considering a single capacitance value. So from 0 frequency to F1 frequency, the gain will be moderate, that is the gain will be normal, the gain will be same. You can observe here, when it exceeds, when the frequency is greater than F1, then the gain is going to decay, and the gain is going to decay, that is nothing but the gain is going to decrease, so when frequency is going to increase. So here you can observe that the gain decrease in the gain value. So this is the frequency response for an operational amplifier. So here you can see the frequency response. So F1 is the corner frequency, and so here F1 is the corner frequency, the gain which is given by AOL divided by 1 plus J F by F1. So the magnitude will be given by AOL divided by root of 1 plus F by F1 whole square. So if we consider the phase angle, so then here we can see this is the phase difference. So the phase angle is going to change from 0 degrees to minus 90 degrees. At F1, it will be around the phase shift of the signal, the phase shift of the signal that we have applied. That means nothing but when we apply a signal, that is going to, the output is going to be phase shifted. So at which angle it is going to be phase shifted? That is nothing but up to F1. Up to F1, there is no, the phase shift will be very small. So and after at F1, you can see that there is a phase shift of 45 degrees, and beyond that there will be a phase shift of minus 90 degrees, minus 45 degrees and minus 90 degrees. For frequency F less than F1, the gain will be 20 log AYL, and for frequency F is equal to Fn, 3 dB down from the DC value. F1 is also called as the corner frequency, and for F greater than for the frequency greater than, very much greater than F1, the gain decreases at a rate of minus 20 dB per decade. So here this is what we are going to discuss. And coming to the phase characteristics, coming to the phase characteristics, F is equal to Z. F is equal to 0, phase angle is 0. So here you can see the phase angle is 0, and F is equal to F1, the phase angle is minus 45 degrees centigrade. So that is, oh, sorry, minus 45 degrees. So that is going to, the signal is, the input signal is going to lag. So sorry, the output signal is going to lag for the, by the input signal around minus 45 degrees. And at F is equal to F is infinity. That means at higher frequencies, the phase angle will be going to be lagging by minus 90 degrees. So it shows that minus 90 degrees phase changes in an op amp with single capacitor. So for by using a single capacitor, there will be a phase shift of minus 90 degrees. So zero frequency is taken as 1 decade below the corner frequency F1. Infinite frequency is taken as 1 decade above the corner frequency as F1. So zero frequency is taken as 1 decade below the corner frequency, and infinite frequency is taken as 1 decade above the corner frequency. And if you consider, so if you write this in a frequency domain, that is nothing but S domain, by using the Laplace transform, you can see that the gain will be given by AOL into omega 1 divided by S plus omega 1. So, but practically, we are having three stages for an operational amplifier. So when we are having three stages, so here we have considered only single capacitor, and we are going to write the equation for the gain. So when we are going to write the equation for the gain using a single capacitor, A is given by AOL into omega 1 divided by S plus omega 1. But practically, we have discussed, as well as already we have discussed that practically for an operational amplifier, there will be three stages. So there will be three stages coupling. That means each stage, when two stages are going to couple, then there will be a capacitance effect. There will be, from this we can know that there will be three capacitance effects. There will be three capacitance effects, which is going to produce the gain, which is going to obtain the gain, as you can see here, the gain equation. A is equal to AOL divided by 1 plus J into F by F1. So which is due to the single corner frequency, that is single capacitance value, can be written as 1 plus J into F by F1. Whereas for other capacitance value, we are going to write as 1 by J into F minus F by F2, and another will be 1 plus J into F by F3. So where F1 is less than F2 is less than F3. So finally, we are going to obtain the gain, which is going to depend upon the overall gain, which is going to depend upon open loop voltage gain into the omega 1, omega 2, omega 3, as well as omega 2 divided by S plus omega 1, S plus omega 2, and S plus omega 3, where omega 1 is less than omega 2 less than omega 3. So from this diagram, you can see here the frequency response for an operational amplifier. So in this diagram, we can consider the we are going to consider, on the x-axis we are going to take the frequency, that is from 1 kilohertz to 100 megahertz. On y-axis we are going to consider the gain, so that is open loop voltage gain, that is AOL, which is in decibels, which is in the decibels. So here you can see from 1 kilohertz to F1 frequency, that is the first corner frequency, the gain is constant. The gain is constant, almost constant. So up to here, the operational amplifier performs better. That means below 1 kilohertz also, the operational amplifier is not going to perform better. So from 1 kilohertz to F1, the operational amplifier is going to perform its the practical operational amplifier. Here we are going to consider the practical operational amplifier is going to perform better. That means the gain will be constant. Whereas after F1, the gain is going to decay. That means the gain is going to fall by minus 20 dB per decade. That means decade means here that is nothing but for every 10 that is for example 1k to 10k, like that, from 100k to 110 or 110k, uh, like that. So decade, for every decade the gain is going to decrease by 20 dB, minus 20 dB. The gain is going to decrease by minus 20 dB. That means uh, here the gain is going to decrease. That's why we are going to consider it as minus 20 dB. Minus 20 dB per decade. That is going to the gain is going to fall by minus 20 dB. Up to f2 it is going to fall minus 20 dB. At f2, yes, this f2 is due to the capacitance effect of second stage. If we consider the second stage capacitance value, then f2 is the corner frequency due to that capacitance value. And here you can see from here to f3, the gain is going to decrease by minus 40 dB per decade. That means the gain is going to fall further. So further the gain is going to fall, and then from f3 to beyond maximum frequencies value, the gain is going to fall by minus 60 dB per decade. So like this, by considering the three capacitance effects, so the gain is going to fall from f1 to f3, like this. So for this reason, for a practical operational amplifier, so the frequency response will be like this. So we can operate, that means we have to understand that the concept is here, we have to understand that the operational amplifier is going to perform much better in this region, that is from 1 kilohertz to 100 kilohertz up to f1. Hmm? So here you can see, so in this frequency range the operational amplifier performance will be better. So beyond this frequency range or below this 1 kilohertz, the operational amplifier is not performing better. So we are having the experiment also, we can do the experiment in our laboratory also. So how to check the performance of operational amplifier means, then we are going to consider a circuit such that we are going to consider the we are going to construct the operational amplifier, and we are going to give the input signal, sinusoidal signal, and then we are going to observe the frequency response output signal in a CRO. You can observe the output signal. If we increase the frequency of the input signal by keeping the input signal voltage constant, we are not going to change the amplitude of the input signal. That means we are not going to change the strength of the input signal, but we are going to change the amplitude of the input signal. Frequency of the input signal. So when we are going to change the frequency of the input signal, so we can observe the output signal in the CRO, input signal as well as output signal. So input signal is going to having the same magnitude value. That means the same voltage value and frequency is going to change. Whereas the output signal, we can observe the output signal. So at frequencies, at low frequencies, the gain will be small, and from 1 kilohertz to 100 kilohertz, the gain will be moderate, and from after 100 kilohertz, that is after f1, we can say that gain is going to fall again, the gain is going to fall. So that means we can observe this by observing the output signal in the CRO by increasing the frequency of the input signal. So by increasing input signal, so you can observe the height of the signal, that is the amplitude of the signal is going to change when frequency is going to change, without changing the input amplitude. Without changing the input amplitude, the output amplitude is going to change. So this is nothing but the effect of this is nothing but the effect of the capacitance values in an operational amplifier. So this is how we are going to obtain the frequency response for an operational amplifier. And now we are going to consider the closed loop. So next, closed loop function of an operational amplifier. So next concept is closed loop function for an operational amplifier. In open loop, Opamp cannot operate linearly. So here, up to now we have considered the open loop function of the operational amplifier. Open loop gain is infinity, nothing but the open loop gain is infinity. So for that reason, so for operating this operational amplifier in linearly, that means in linearly means we are going to use this operational amplifier for several applications, like it can be used as an amplifier, it can be used as an oscillator, so it can be used as a logarithmic amplifier. It can be used as an A to D converter or D to A converter. Like this, several applications. For several applications, we are going to use this operational amplifier. So mainly is many applications is going to, in many applications we are going to consider op-amp in a closed loop configuration. That is closed loop configuration. That means why we are going for closed loop configuration means in open loop configuration, so the gain will be infinity. There is no stability in that. There will be the op-amp will be not stable. That means the op-amp is not going to produce we cannot control the gain of the operational amplifier. If you want to control the gain of the operational amplifier, that can be controlled with the help of feedback only. So by providing the feedback resistance, here you can see from this circuit, here from this circuit you can observe that the feedback resistance, we are going to consider the feedback resistance here RF. So when we are going to consider the feedback resistance, there will be a control on the input signal. Whatever the input signal we are giving, there will be a control on the input signal, and this control will provide that means will be will going to modify the gain of the operational amplifier. So for that reason, we are going to consider mainly in several applications we are going to consider the closed loop configuration of the operational amplifier for a linear operation of an operational amplifier. So we are going to consider this feedback resistance RF, and we are going to consider this closed loop function of the operational amplifier. The feedback does not allow operational amplifier to operate in saturation region, and it allows the op-amp to operate in linear region only. That means it is the now the op-amp is going to operate in linear region. So for that, what are the factors is going to affect this closed loop when we are going to consider this closed loop function for an operational amplifier? So what are the different factors is going to affect the operational of the that is the performance of the operational amplifier? So we are going to see now. So here we are going to consider op amp as a non-inverting amplifier. So when we are going to consider op amp as a non-inverting amplifier, here we are going to consider the closed loop configuration. This is the circuit we are going to use here. So for in this circuit, you can observe that we are going to give the input signal to a non-inverting terminal, that is a positive terminal, and we are going to provide the feedback for inverting terminal through a feedback resistor RF. Mm. And here AOL is nothing but the open loop voltage gain, and beta is the transfer function. So here the beta transfer function can be obtained by R1 in parallel with RF. That is nothing but R1 into RF divided by R1 plus RF. So here we have written that beta is equal to R1 into RF divided by R1 plus RF. So here we are going to consider this the block diagram for this circuit. So this is a block diagram for this circuit. In this block diagram, you can see this is an operational amplifier, and this is the feedback which we are going to provide. So this is the input signal we are going to give, and this is the feedback we are going to provide. That is through beta factor. That is the transfer function of a feedback. And this is the operational amplifier which is having a open loop voltage gain AOL, and we are going to obtain the output here. So here we are going to consider this node as X, and X is nothing but the difference between the input voltage and the feedback voltage. That is what we are going to write here. So X is nothing but the difference between input minus the feedback voltage. Feedback voltage is nothing but V naught into beta, which is nothing but V naught into beta is our feedback voltage. So this is going to obtain as the input to the operational amplifier, and with that input signal we are going to obtain the output. So with reference to the block diagram, by solving, we have the gain V naught by Vn is equal to AOL divided by 1 plus AOL into beta. AOL into beta is the loop gain. AOL into beta is the loop gain of an operational amplifier. So for this we are going to the signal. We are going to observe this in this configuration. Closed loop configuration. Here you can see this closed loop configuration. So for this closed loop configuration, we are going to X, as we have discussed that X is equal to V in minus V naught into beta. V in minus V naught into beta. Nothing but V naught into beta is nothing but the feedback factor, and V naught is given by, from this equation we can write V naught is equal to X into AOL. So V naught is equal to X into AOL, nothing but. From this block diagram, we can write V naught is equal to X into AOL. X is given by V naught by AOL. So the equation 1, this equation 1, we are going to substitute this X value in the equation 1. So by obtain from this equation 1, we can write V naught by AOL is equal to V in minus V naught into beta. In the place of X, we are going to write V naught by VA. So V naught by V in. So we are going to obtain finally V naught by V in. So V naught by V in, by solving this equation, we are going to obtain V naught by V in, which is equal to AOL by 1 plus AOL into beta. So open loop voltage gain divided by 1 plus AOL into beta. This is the closed loop voltage gain. So this V naught by V in, which is called as a closed loop voltage gain. So see here, in this closed loop voltage gain, you can observe that mm, that in the denominator we are having 1 plus AOL into beta, so which is nothing but the closed loop voltage gain, and here AOL into beta is the loop gain. AOL into beta is the loop gain. So the stability, mainly the stability depends upon the roots of the characteristic equation. So here the characteristic equation is 1 plus AOL into beta, so which is equal to 0. Then AOL into beta, the loop gain is equal to minus 1. So the complex form, in complex form we can consider so the real part as well as the imaginary part. So for that reason here, in the above equation, in this equation AOL into beta equation, so there will be no imaginary part. So we are going to consider imaginary part as 0, and we are going to write here imaginary part, that is AOL into beta is equal to minus 1 plus J0. So AOL into beta, if you consider the magnitude, then we are going to write it as root of minus 1 whole square plus 0 whole square. So we will get that magnitude of the loop gain, which is equal to 1. So when loop gain is equal to 1, the op-amp is going to provide a sustained oscillations. You know that. So that means it is going to provide oscillations. In fact, it must act as an amplifier. So but here, because of this closed loop function, that is because of this closed loop, so here AOL, that is loop gain, becomes unity. When this loop gain becomes unity, so then that circuit is going to become is going to act as an oscillator instead of acting as an amplifier. So here we are going to consider op amp as a non-inverting amplifier, but here it is going to act as an oscillator. So this is nothing but a unstable condition. This is nothing but an unstable condition. So we have to make this op amp uh, stabilize, make this op amp stabilize. So how we are going to stabilize this operational amplifier? So that depends upon this beta value, that depends upon this AOL, that open loop voltage gain, and the beta value. So for this we are going to consider the open loop voltage gain as well as the beta value at a so here you can see the angle, and we consider the angle AOL into beta is equal to tan inverse of 0 by 1. So AOL into beta is equal to 0. At a particular frequencies, both conditions may be satisfied, and hence the amplifier begins to oscillate. So it becomes unstable. So this is the condition. So the amplifier is going to not going to act as an amplifier. It is going to oscillate. It is going to produce oscillations. So how we are going to how this amplifier is going to stabilize? So that concept will be studied in the next topic, that is stability of an operational amplifier. So next, in the next class, we are going to discuss about that. So with this, we are going to complete this session. Thank you, students. In the next class, we are going to see the operational amplifier stability, how to stabilize that on our operational amplifier.